Hey guys, welcome back. So today we're going to, as usual, go over some homework for the homework from day 4, and then I'm going to talk a little bit more about instantaneous rate of change and introduce something called the derivative. Actually, you've already seen the derivative, but I haven't called it that yet. So I'm going to turn on my document camera, and I'm going to go over all of number 1 from the homework. So this is actually my notes from the last worksheet, but just to remind you guys, the formula that we spent all of last time sort of understanding is this guy right here. It's that the instantaneous velocity at time c is given by this. This assumes, of course, that the function f represents position, right? If f is a function of position, then you apply this formula and you'll get the instantaneous velocity at c. So in number 1 on the homework, we're told that we have a rocket. It's flying around, and its position function is given by x squared minus 8. X is measured in seconds, and the function is measured in feet. So part A, they would like you to find the average velocity over the time interval 2 to 4. So we want the average velocity over the time interval 2 seconds to 4 seconds. I'm just going to write that like this. This funny notation here, you've seen it before at some point in your life, but maybe it's been a while. This refers to the interval from x equals 2 to x equals 4. It's like a range of values. So it's an interval of time, right? It's the interval of time from 2 seconds to 4 seconds. That's what this bracket notation means, just to remind you. So the average velocity, okay, average velocity is not a limit, right? Average velocity is this thing that you've been computing since, whatever, elementary school. It's just distance traveled divided by time elapsed. Of course, the distance traveled over this time interval is just going to be f of 4 minus f of 2, right? I mean, that's the position that the rocket winds up at minus the position that it started at. That difference will be how far it went over that time interval divided by 4 minus 2, right? So change in position over change in time, that's the average velocity. So we just have to compute this. What is f of 4? Well, if you plug 4 into this, it's 16. So 16 minus 8 is going to be 8. Minus f of 2, what's f of 2? Well, you plug 2 into that. 2 squared is 4. Minus 8 is negative 4. So it's going to be 8 minus negative 4. Watch out for that double negative. Divided by 2. So that's 8 minus negative 4. That's like 8 plus 4, which is 12 over 2, which gives us 6. Okay, and the units would be feet per second. Okay, and then B, average velocity. Again, it's average velocity, but this time over the time interval from 2 to 2.01, so a much shorter time interval. That's going to be f of 2.01 minus f of 2 over 2.01 minus 2. Change in position over change in time. This I probably need a calculator for. 2.01 squared minus 8. Let's see what that would be. 2.01 squared minus 8 is negative 3.9599. And then minus f of 2, we already saw that f of 2 is actually negative 4. So that's minus negative 4. Again, be careful with those double minus signs. Over, 2.01 minus 2 is obviously just 0.01. So what is this going to be? So negative 3.9599 minus negative 4, that's like plus 4, divided by 0.01 gives us 4.01 feet per second. And then finally, in part C, we're being asked for the instantaneous velocity at the time 2. Okay. Now, first of all, notice that we just computed the average velocity over a time interval containing this moment, and a very short time interval as well, right? And we got 4.01 feet per second. So we should expect that the true instantaneous velocity at 2 is going to be very close to this number, right? Because this interval is very small and it contains the time 2 seconds. And so therefore we should expect this number to be very close to the instantaneous velocity at 2. So I wouldn't be surprised if it turns out to be 4. But to find out, we have to use this formula, right? This is instantaneous velocity, so we need to take the limit as x approaches. Well, let's remember, the instantaneous velocity at time c is given by this. I'm looking for the instantaneous velocity at time 2, so I'm going to take the limit as x approaches 2, f of x minus f of 2 all over x minus 2, and I just need to compute this limit. So what is this? This is the limit as x approaches 2. Okay, f of x is, of course, just x squared minus 8, right? It's just the function itself. What is f of 2? We've already seen multiple times that f of 2 is -4, so it's minus -4. Be very careful with that double minus over x minus 2. So that's the limit as x approaches 2 of, so it's -8, but then it's minus -4, so it's like -8 plus 4. So it's like just -4 in total. So the numerator is x squared minus 4 over x minus 2. Now, this is an algebraic limit. Technically the first thing you should try is just plugging in the number, like try plugging 2 into this. I promise that if you do, you're going to get 0 over 0. So this thing does have to be simplified before you can evaluate the limit. So what can you do? Well, the numerator can be factored. It's a difference of 2 squares, right? X squared minus 4. 4 is a perfect square. That's going to factor as x plus 2 times x minus 2 all over x minus 2. As you can see, these x minus 2 factors will cancel. Okay, so those cancel. And we're just going to be left with the limit as x approaches 2 of x plus 2. And now that we've simplified the expression, if we just plug 2 into this thing, we get 2 plus 2, which is indeed 4, pretty much what we were expecting given this guy right here. So 4 feet per second is in fact the instantaneous velocity at 2 seconds into the trip. Okay, great. Now, the other thing I wanted to mention, of course, is that later on in the worksheet in exercise 3, there's a fair bit of reading that I put in there, some notes and explanations. And basically, it is all about instantaneous rate of change and average rate of change. So here's the idea. All of yesterday, we talked about average rate of change, average velocity versus instantaneous rate versus instantaneous velocity, right? Average and instantaneous velocity. Now, I want to be clear. Velocity, as I told you in the worksheet, is the rate of change of position, right? The word velocity really just means how quickly your position is changing. Okay, it's the rate at which position is changing. So velocity is the rate of change of position. Now, we can talk about the rate of change of anything. We can talk about the rate of change of position, which is what velocity is. We can talk about the rate of change of temperature, like how quickly the temperature is going up or going down. We can talk about the rate of change of population, like how quickly a population, say of people, is increasing or decreasing, right? We can talk about the rate of change of pressure in the atmosphere, or rate of change of gross domestic product in the economy. We can talk about rate of change of anything, okay? And just like rate of change of position, that is to say, just like velocity, there's always 2 versions of rate of change. There's average rate of change and there's instantaneous rate of change, okay? Just like there is for velocity. Everything that we said about velocity, which is the rate of change of position, translates perfectly to rate of change of anything else. So if we want to talk about rate of change of temperature, we can talk about an average change in temperature, which would simply be, the change in temperature divided by the change in time. like how long the change in temperature took. Or we can talk about the instantaneous rate of change of the temperature, like how quickly is the temperature changing at this very moment. Or take population. We can talk about average rate of change of population, which would simply be total change in population divided by how long it took. That would be the average rate of change of population. Or we can talk about instantaneous rate of change of population. That would be how quickly the population is changing at this very moment, not over a period of time. So everything we said about average rate, average velocity and instantaneous velocity translates perfectly to any other kind of rate of change that we want to think about. And the formula that we derived for the instantaneous velocity is actually the formula for the instantaneous rate of change of any function. Okay, no matter what the function describes, whether it describes, population or temperature or whatever. So just to be clear, we have average rate of change, right? So let's let f be any function. Maybe f represents position, or maybe it represents temperature, or maybe it represents population or whatever. Average rate of change over the time interval, let's say a to b. Okay, that's given by the change in the value of the function, which is f of a minus f of b over b minus a, right? Notice what this is. This is the change in the value of the function. It's like the value of the function later minus the value of the function earlier. That's how much the function changes from time a to time b. And then this bottom number here, if you're talking about the time interval from time a to time b, well, then b minus a is how long that time interval is. So that's the average rate of change. It's the change in the value of the function divided by the change in, how much time elapsed. On the other hand, and that's sometimes abbreviated like AROC, average rate of change. And then on the other hand, we have the instantaneous rate of change. And that's not something that's computed, over a time interval, but rather at a particular moment. So it's the instantaneous rate of change at a point, let's say at time c. And that, of course, is given by the limit as x approaches c, f of x minus f of c over x minus c. And sometimes that's abbreviated IROC, IROC, okay? So that's sort of what we talked about in exercise 3 in the previous worksheet. Now, the instantaneous rate of change. Is a really, really important concept. In fact, you'll spend like months really sort of unpacking and trying to understand this concept when you take calculus. Because it is such an important concept, and this is true for lots of things in math. When there's an idea that is really profound and really important, it tends to have a lot of different names. Like it goes by different names. And there are usually a lot of different ways of seeing it. If you have a really deep, profound, important concept, then it has lots of different names and lots of different ways of understanding it, lots of different ways of looking at it. And so what we're going to be doing today and over the next couple of days is looking at a few different ways of describing the instantaneous rate of change. We're going to be looking at the instantaneous rate of change from a couple different perspectives. Today, I'm really just going to introduce a new word for this thing, okay, a new word. It's called the derivative. All right, so here's the definition. The instantaneous rate of change of a function f at a time c is also called the derivative of f at c. Okay, I want to be clear. I am not defining anything new. Like instantaneous rate of change is something that you saw in the worksheet yesterday. It's right here, and this is the formula. And all I'm telling you is that this concept sometimes is called the derivative of f at c, but they mean exactly the same thing. Okay. Now, in mathematics, we like to use symbols to abbreviate things, right? We don't like writing whole long paragraphs. We instead like to use symbols to represent ideas. And this idea, the instantaneous rate of change at c, or if you like, the derivative at c, we have a symbolic representation for it, okay? And here's what it is. So in symbols, it's written, okay, so here's the symbolic way of representing the derivative of f at c. You write f, and then you make this little hash mark here, like this little mark here, it's like an apostrophe. It's technically called a prime of c. All right, so this thing is pronounced f prime of c. That's how you pronounce that expression. Okay, so, instead of writing the phrase derivative of f at c or instantaneous rate of change of f at c, instead of writing all of that, which is kind of a long phrase, we just write this symbol right here, f prime of c. And that means the derivative of f at c, or if you like, the instantaneous rate of change of f at c, okay? So, I want to be really clear because, we introduce all these different ways of seeing the derivative, and I'm going to introduce another one in the next lesson and another one after that. And students get quite confused. And it has to be emphasized over and over again that all this stuff means exactly the same thing. So let me just take a moment to make it really clear that every one of the following things means exactly the same thing. So here's kind of a summary. All of these mean exactly the same thing. All of the following phrases, expressions, formulas, symbols, they all mean exactly the same thing, okay? Instantaneous rate of change of f at c. That means exactly the same thing as the derivative of f at c, which means exactly the same thing as this symbolic expression here, f prime of c, which, and all three of these are given by the exact same formula, limit as x approaches c, f of x minus f of c all over x minus c. All four of these things, 1, 2, 3, 4, they all mean exactly the same thing. They're interchangeable. They're just different, So if you want to compute the instantaneous rate of change, you use this formula. If you want to compute the derivative, you also use this formula because they're the same thing. If you want to compute this guy here, well, that is just the derivative. They're all the same thing. So again, you use this formula. Yeah, so just to be clear, they all mean the same thing. So let's just do a couple of examples and then we'll be done. We have a much shorter lesson today. Last time was pretty brutal, right? Like an hour. I know that was intense, but instantaneous rate of change is not a trivial concept, and it takes a while to wrap your head around. So I'm just going to do two examples. Okay. So example 1. And this is really just practicing a notation more than anything else. Let's let f of x be the function 5x squared. It's kind of a lousy looking 2, but I think it's clear. So 5x squared. And what I want to do is find f prime of 3. Okay, so what does that mean again? Well, let's think. F prime of 3, that's the same thing as the derivative of the function at c. It's the same thing as the instantaneous rate of change at 3. And it's all given by this limit formula, right? So I take the limit as x approaches, well, c in this case would be 3, right? Like looking at the formulas, the number that appears here, that's your c. And for the formula, you take the limit as x approaches c. So it's going to be the limit as x approaches 3, f of x minus f of 3, all over x minus 3. Okay, so all right, so let's unpack this. What does this mean? So f of x is, of course, just 5x squared. Minus, and then what is f of 3? We can probably do this in our heads, right? If you plug 3 into this thing, 3 squared is 9, and then times 5 is 45. So that's 45, all over x minus 3. Now this is an algebraic limit. If you want to evaluate it, technically you should try plugging 3 into this thing and see what you get. I promise you get 0 over 0. If you get, right, I promise you get 0 over 0 if you plug it in. So this thing needs to be simplified before we can evaluate the limit. The numerator can be factored. First of all, there's a common factor that can be removed, right? See the 5 and the 45? There's a common factor of 5 that can be removed. So x squared minus 9. And then x squared minus 9 is a difference of 2 squares, right? It's one thing squared minus another thing squared. That can be factored further. So it's going to be 5 times x plus 3 times x minus 3. All over x minus 3. And as usual, after factoring, we see that there is some cancellation that can be done. So this guy is going to cancel with this guy. And that's going to leave us with limit as x approaches 3, 5 times x plus 3. And now that we've simplified our expression, we can just plug the 3 in. And if we do, we're going to get 5 times 3 plus 3. That's 5 times 6, which is 30. So that's the instantaneous rate of change of this function at 3. Or if you like, it's the derivative of this function at 3. Now what does this mean? Well, without knowing what the function f represents, it's a little hard to say. I mean, roughly speaking, this says that, every time x increases by 1, this function increases by 30, roughly. That's kind of what it's getting at. But yeah, if this function represented position, like the position of an object, well, instantaneous rate of change of position is just instantaneous velocity, right? So if this function represented the position of an object over time, then this number would just be its instantaneous velocity at 3 seconds or whatever, okay? But if this function represented the population of some species, then this would be saying that, at 3 units of time, the species population is increasing by 30 whatever organisms per year or something, right? Or if this function represented temperature, then this number would represent, it would be saying that 3 hours in, the temperature is increasing by 30 degrees per hour or something, right? Whatever. So it's hard, can't really say exactly what it means without knowing what F represents, but I hope that gives you kind of an idea about what instantaneous rate of change is all about. So, okay, so with the second example, I'm going to give you a problem that shows up a lot in the AP exam, but it's a good problem because it sort of tests your understanding. So here I'm going to write down a table of values here. I'll explain what this means in a moment. For 6.25, 12.25, and 16. So, okay, so here's what I have. This is a brand new problem. The function f is not the same as the function over here. It's a brand new problem. It's a brand new function. In this case, f is an unknown function. As in, like, I don't have a formula for it. I don't know what it is. Maybe it's x squared plus 1 or something, or I don't know what it is. It's just some function, okay? So I don't have a formula for this function. Instead, all I have is a table of values. I know that when x is 2, the function's value is 4, and when x is 2.5, the function's value is 6.25, and so on. So that's all I know. Actually, it looks like maybe the function is just x squared, but let's pretend we don't notice that. Let's just pretend that f is a mystery function, okay? And anyway, we can't be sure. So here's the question. I want to approximate f prime of 3. In other words, I want to find the derivative of the function at 3, or alternatively, the instantaneous rate of change of the function at 3. That's what I want to find. And notice I use the word approximate. Why approximate? Like, why not find it exactly? The thing is, without knowing the formula for this function, I actually cannot find the instantaneous rate of change. I can't find f prime of 3 without knowing the formula, because, the formula for instantaneous rate of change is this limit, right? Is this guy right here. And in order to evaluate that limit, you've got to know what f of x is. And I don't know what f of x is in this case. At least I don't know for sure. So I really can't use that definition, but I can approximate f prime of 3. How? Because remember, back yesterday when I introduced instantaneous and average velocity, remember that average velocity approximates instantaneous velocity, right? Remember that? And the shorter the interval of time, the better the approximation. Remember that? The same thing is true for any kind of rate of change. So the average rate of change of a function is always an approximation of the instantaneous rate of change of the function. So what I'll say is that the average rate of change approximates the instantaneous rate of change. This guy, of course, is the instantaneous rate of change. This is the instantaneous rate of change at 3, right? Now, from this table, although I can't compute the instantaneous rate of change, I can compute the average rate of change from these values. Okay, let's see how. Like, for example, if I wanted to compute the average rate of change, this is just an example. If I wanted to compute the average rate of change over the interval, 2 to 4, right? From x equals 2 to x equals 4. That would be f of 4 minus f of 2 over 4 minus 2. In other words, it would be, the change in the value of the function divided by the change in, you can think of it as time. And from the table, we know exactly what f of 4 is. F of 4 is 16. And we know what f of 2 is. It's 4. So 16 minus 4 over 4 minus 2, that's 12 over 2, which is 6. So the average rate of change over this interval is 6. Okay. Now, because this interval contains the moment 3, this is actually an approximation of the instantaneous rate of change at 3. So you could say that 6 is an approximation of the thing that we want. Okay. But remember that the smaller the interval, the better the approximation. Okay. So, I computed the average rate of change over 2 to 4, but you could obviously compute the average rate of change over lots of other intervals. You could have computed it over the interval from 2 to 3.5, or the interval from 2.5 to 4. It's lots of different intervals that, over which you could compute the average rate of change. So the question is, which interval should you use? I've already said several times that the smaller the interval, the better the approximation, right? So that's one guideline. You want to use the smallest interval that you can. 2 to 4 is actually kind of the largest interval that we could use, so it's kind of a bad approximation. The other, well, there's one requirement. 3 has to be inside your interval. Has to be inside your interval. So if you did 3.5 to 4, that's like really not a good idea, right? That's like using, remember the car example, right? Like the car trip, that would be like computing your average rate of change for some period of time when you're on the highway and trying to use that to estimate the instantaneous rate of change, when you were in the parking lot. That's a bad idea. The interval over which you're computing the average rate of change has to contain the moment at which you're trying to find the instantaneous rate of change. So whatever interval we use, 3 has to be inside of it. Okay. Ideally, this number should be in the center. That's kind of the gold standard. Ideally, to get the best estimate, you want 3 to be in the middle of your interval, and you want your interval to be as small as possible. So what interval, right, looking at these x values, what interval has 3 as its center and is as small as possible? Well, this interval here has 3 as its center, right? 3 is right in the middle between 2 and 4. But actually, you can do better. This interval right here, 2.5 to 3.5, that has 3 right in the middle, and it's smaller. That's the best one that you can do. So you should use that one. Okay, so a better approximation is going to be obtained by doing the average rate of change from 2.5 to 3.5. That's just going to be, by definition, f of 3.5 minus f of 2.5 over 3.5 minus 2.5. F of 3.5 is 12.25. F of 2.5 is 6.25. And then 3.5 minus 2.5 is 1. And oh, is this just 6? Okay, well, that's kind of silly because it's the same number that I got from this one. Typically, that's kind of a fluke. Typically, these two numbers, will not be the same, and this number will be a better approximation of the true value, but just by a fluke, they happen to be the same. So yeah, so sometimes we'll give you a table of values, and we'll ask you to approximate the instantaneous rate of change. And you can do so by computing the average rate of change over an interval containing the point of interest. Ideally, the interval should be as small as possible, and it should have the number in its center. Sometimes you can't do it, like I think in the problem on the worksheet, there's a problem where there is no interval containing the value at its center, and in that case, you just do the best that you can, as you'll see. But I think that's it for today. Yeah, that's it. So, okay, so yeah, so we can conclude in this problem that f prime of 3 is probably approximately 6. Can't know for sure because we don't have a formula for this function. It looks like it's x squared, but you actually can't be sure. Like it might just look like x squared, but actually be something else. Okay. All right. Well, that is it, guys. All right. See you next time.